And Sir has been one of a few resource persons who has been supportive throughout for this FDP. And always, Sir is a very famous speaker as far as IBM quantum computing is concerned. And he is also an IBM Qiskit advocate, mentor, and an educator. Now I invite Purnima to start the session and introduce our chief guest for today.
Good evening and welcome to day 2 of our ATAL online 6-day faculty development program on quantum computing and quantum machine learning for sustainable solution. We are now starting our third session on topic Introduction to Designing Quantum Circuits. It's my pleasure to introduce our expert Dr. Jayakumar Vaidya. Dr. Jayakumar is a CEO and founder of Anudantra Private Limited. He is also a represented IBM Quantum Educator and Qiskit Advocate Mentor, playing a key role in building the quantum community in India. A senior IEEE member, he has over 15 years of experience in R&D and community in India and has published more than 15 research papers. He has shared his expertise by conducting over 300 quantum programs across India, USA, Russia, and Armenia. He is also a SWAYAM NPTEL portal instructor for All India Council of Technical Education, AICTC, and Department of Science and Technology, DST, which launched India's first undergraduate minor program in quantum technologies. Please join me in giving a warm welcome to Dr. Jayakumar Vaidya. The virtual floor is now yours, sir.
Thank you so much, ma'am. Thanks for this wonderful opportunity. Uh, I really appreciate the organizer, Professor Dr. Deepa Jose, for inviting me. So today's topic is somewhat interesting, right? Today's topic, we're going to create a quantum circuit using IBM Qiskit tool or framework. Okay. So let me introduce myself in sense to quantum community. Okay. So I started my journey as an IBM quantum educator before 5 years. Okay. So each and every year, IBM conducting so many open source challenges. So if you are interested, please take a note about IBM quantum challenges. Who are above 18 years, they are able to enroll these challenges. The second good thing, if you want to have a strong foundation, you can look for IBM Quantum Summer School, which will happen for 2 weeks. Okay, they will put call for the summer school, entirely absolutely free of cost. So challenge is free of cost, summer school is free of cost, and the main thing is about IBM Quantum is about open source. So anybody able to contribute, anybody able to participate, they can develop the source code of this entire framework. The next good thing is about certification. So if you're looking for strong career in quantum, you can go for IBM Qiskit certification. So many corporates are there, MNCs are there, but only IBM is offering industry level certification. Okay, so Google is there, Microsoft is there, Amazon is there. Okay, so many big MNCs are there, but only IBM is offering industry level certification. So across the globe, less than 1,000 people clear this certification. Across India, less than 200 people clear this certification. Okay, so they revamp the certification in next level. So look for the newest certification they are about to release in September 30. So I will share that link with you. IBM Skit certification. They not yet released, but you can have a look how it is designed. So this is the latest certification where you can look. So exam contains 68 questions. So you need to pass 47. Okay. For this exam, whatever we're going to conduct today, it will help you to clear certification. Okay. We're going to create quantum circuit, which is the third topic in this certification. Okay. Before that, we need to understand what are the quantum operation, quantum gates. Then we need to go for uh, creating quantum circuits. Okay. I try to uh, cover the basic stuff. So within 1.5 hours, we are not able to cover entire thing, but at least we can have a glance about how to create a quantum circuit. So once you have this certification, once you clear this certification, then you can look for advocate. So this is a honorary post. So once you completed certification, you can go for advocate post. Okay. So once you become IBM Qiskit advocate, you can ambassador the software. Okay. You can become an ambassador for the software. You can promote this. You can create awareness about the software. Then you can look for internship. So once you become IBM Qiskit advocate, they will give internship for you about 3 months. So this is very good chance to get into industry. Once you completed internship, you can act like a mentor. So minimum 5 years of experience needed for mentor. So most of the faculty are eligible. And you can look for free IBM quantum courses. So all these courses are very excellent resources. You can start from basics of quantum information. You can start from basics of quantum information. If you're interested in cryptography, you can go for quantum safe encryption and quantum safe cryptography. If you're interested in doing business with quantum industry, you can look for quantum business foundation. So people who are involved with MBA, they can also able to join in this course. Okay. If you're interested for uh, quantum machine learning, you can look for variational algorithm design. I'll share that link with you if you're interested. So Google IBM quantum learning. I think I kept my audio in full level. Full level. Please check at your end.
It is audible, sir. It is very clear. Yes.
Yes, ma'am. Yes, ma'am.
Yes.
Yeah. So go to this link, IBM quantum learning. So you will have variety of course. So suggestion from one, basics of quantum information. Then once you completed, you can go for fundamental of quantum algorithm. So how we are writing algorithm in classical, you can write algorithm using quantum, right? Then you can go for general formulation of quantum information. Once you completed all this stuff, you can go for quantum error correction. Once you completed, you can go for quantum computing in practice. Okay. So for an example, if you click first course, so each and every course designed with multiple module. So they will give a clear instruction what to do and what are the courses you need to complete after this. What is the recommended background needed for this? Okay, linear algebra, you can get linear algebra from Khan Academy or some books. Okay, they give each and everything. Okay, so once you completed course, you will get digital batch like this. More digital batch if you are able to acquire, more recognition you will get from the industry. Not only from the industry, if you're applying for any funding, it will help you to prove your expertise. Okay. So for an example, if I'm clicking the first topic in the first module, so it will contain a YouTube video. So YouTube video will pop up and you can download slides for this topic. Otherwise, you can study from the text material. So multiple way you can do. Either you can go for video or either you can go for slides or either you can download notebook. So this is the Python Jupyter notebook. So whatever you are preferable, you can go with all this stuff. Okay. So if you want to study through this video, each and every video is literally tough for each and everyone. So nobody in this world able to understand everything from a single watch. You need to watch multiple times. Okay. So my strong advice, if you want to study quantum, you need to have a lot of patience. Okay. So click this video. Whenever if you find any unfamiliar word, stop that video right there. Go to Google, do some basic stuff, research, come back to you. So you need to study quantum only in this slow phase. Okay. Because quantum involved with a lot of mathematics, lot of physics. You cannot skip each and everything. Okay. It is like mathematics. So you need to go very slowly, very steadily. So you need to study multiple times. So this is the only way to learn quantum. So once you completed, what you can do, you can look for other courses. You can look for other courses. Once you completed foundation, you can look for focus topic like quantum machine learning, okay, quantum chemistry, quantum diagonalization algorithm. Depends upon your domain, right? So if you want to teach quantum in your classroom, you can look for these two modules. So they beautifully develop each and everything. Lot of tutorials is there, lot of documentation is there. Okay. To complete today's task, so go for this. Go to this link. Try to create a login if you don't have. Okay. Use your Gmail account. Continue with Google. Okay. Sometimes it will ask credit card for the verification. So if you are comfortable, try to give the credit card details. Otherwise, without credit card, you can use this tool. Without credit card, you can use this tool. So I already created login. Once you have login, it will show in this way. Okay. So click Composer. Click Composer. I will share this link with you. Even though if you don't have any credit card detail, you can use without login also. So click this link, Composer. Yeah, I shared certification, learning, also login creation, also Composer. So I recommend each and every one of you don't log in through your mobile. Please log in through your laptop or your CPU. All of you able to log in this platform Composer? Once we are in same level, we can proceed. So please put in chat box, all of you able to launch Composer. Even though if you don't have account, you can log in Composer. You can use Composer without login.
As sir told, you can put in the chat box if you have got the link so that you can do it parallel, no, sir?
Yes, ma'am. Parallelly they can
Yeah.
do.
Yes, yes.
Please put in chat box. Are you able to access Composer just like me? Okay, very good. Thanks, ma'am. So at least one participant need to respond. Otherwise, so one more tool I want to introduce. This is open board. This is open board. This is very useful for you if you are teaching open board. So simultaneously you can use application and you can write over your application wherever, whenever if you want. Okay, just like this. And you can use eraser. This is very useful for because it is open source, open board. Okay. So before understanding QuizKit, we need to understand what is a quantum beam. So for that, we need to understand what is a block sphere. Okay. So block sphere is a sphere. Block sphere is a sphere which contains radius equal to 1. So it makes that sphere in as a unit sphere. Okay, like a unit circle, it is a unit sphere which will make everything systematic. Okay. We are dividing the sphere into two levels, two hemisphere. It will divide exactly in the equator, two halves. Why we are dividing into two halves? Because we need to represent binary system, or you can say two level system. So our input data is binary data. Okay, it represents two level system. So that is why we call it qubit. Okay. So in this qubit, in this block sphere, what we are doing, we are taking the origin point. From the origin, we are creating Cartesian coordinates, Cartesian axis. Okay. So three coordinates based upon 3 points, x, y, z. So this is what we are doing in this sphere. Okay. And we are taking two extreme points. So these two extreme points are like polar points. Okay. So this point is extreme for North Pole, or you can say northern hemisphere. So this is extreme for northern hemisphere. Okay. This is South Pole. This is South Pole. And this is extreme for southern hemisphere. So we have 2 points. Okay. We have 2 points. And we are mapping these 2 points to our physical system. So we are taking a mathematical model, block sphere, and we are trying to associate our physical value over this block sphere. Okay. So take an example of binary value 0. So whatever I am writing inside code, it is binary value. So these two are binary value. We try to associate this binary value, okay, to quantum state, So this is state 0, this is state 0, and this is state 1. This is state 1. Okay. So we can make a difference between binary value and quantum state. Whenever if you are looking this symbol, this is quantum state. This is quantum state. Okay. There are two different representation in quantum state. So this is called ket notation. This is called ket notation. So what is the meaning of ket notation? Suppose if you have state 0, we can represent in this way. So this is called ket 0. Okay. So if you want to represent quantum state 1, okay, you can represent in this way. So a bar followed by greater than symbol. Okay, remember this. So this is ket 0, ket 1 representation in the block sphere. We try to associate the physical value over the mathematical abstract uh, representation. Okay, these polar points are called pure states. These polar points are called pure states. We try to associate our binary value over these quantum states. That is why it is pure. That is why it is pure. Okay, so take a random point. Take a random point in your block sphere. Okay, imagine this green dot. Green dot represent your quantum particle. Your quantum particle could be electron, ion, photon, neutron, could be any subatomic particle. So imagine this green dot is any subatomic particle. Any subatomic particle. And what we are doing, we try to generate a vector from origin. We try to generate a vector from origin. This will represent your quantum state. This will represent your quantum state. Okay, mathematically what we call quantum state vector. So this will give information about your quantum particle. Information about your quantum particle. So whatever particle you are using as a qubit, so this will give information. Okay. So if you want to know your quantum particle, definitely you need to know where your quantum state vector pointing. So whenever green particle moves over your block sphere, okay, this quantum state vector also moves. Okay, it is like synchronized action. It is like synchronized action. Okay, so this point is technically called mixed state, or you can say superposition state. Superposition state. So what is the meaning of superposition? One position over another position. One position over another position at the same time. At the same time. So this is the meaning of superposition, or you can say mixed state. So both are synonymous. Both are synonymous. Okay. So I try to cover from previous slide. So we have 2 points. These points are called extreme points, polar points. So this will represent your pure states. So state 0, state 1. Okay. Take any random point in your block sphere, anywhere in your block sphere, inside your block sphere. This will represent mixed state or superposition state. Okay. So if you try to slice your sphere in this way, okay, this will form x dash and y dash plane. So this is your xy plane. This is your xy plane. And this is a parallel plane to your quantum particle. Okay. So what we are doing over here, we try to do a projection. We try to do a projection from quantum particle, I will say quantum particle as QP towards XY plane. So this will have some intersection. This will have some intersection. Okay. From this point, again, you are doing a projection. Again, you are doing a projection. You are doing a projection towards origin. Towards origin. Okay. So this will form a right angle triangle. Right angle triangle. So once you have right angle triangle, you can apply trigonometry. You can apply trigonometry. Okay. Just I try to recall. So we have a quantum particle. Okay. From that quantum particle, we try to slice the sphere x dash y dash plane. From that point, we are doing a projection towards xy plane. Okay. It will do intersection. from that intersection, you try to do a projection towards your origin. So this will form a right angle triangle. Once we got right angle triangle, we are able to apply trigonometry. Okay. So trigonometry always dealing with three angles. So one angle be able to derive from z axis to your quantum state vector. So this is first angle. This is first angle. Okay. In the same way, it will generate an angle between your x axis to your downwards projection. This is your second angle. So what is the first angle? Theta. What is the second angle? Psi. Okay. So we got two angles. We got two angles. What we can do? We can convert Cartesian coordinate sorry about that, coordinate into polar form. So what is the polar form? It represents two angles, or you can convert in angular form. You can convert in angular form. Okay. So consider state 0 and state 1, both are opposite to each other. Both are opposite to each other. So how to represent in polar form of opposite two signals or opposite two entity with the help of cos and sine. So these two are opposite to each other. These two are opposite to each other. Okay. So try to look slowly. So previously we have three Cartesian axes. So from x, y, z, we converted into two angles. Okay. From the two angle, we are able to represent in polar form. Okay. So this is your superposition. This is your superposition. Okay. Which will represent your quantum particle. Which will represent your quantum particle. So if you want to define your quantum particle, you can represent in the form of superposition. Okay. What is the meaning of superposition? It is the linear combination of state 0 and state 1. So look at here, and we are doing addition. We are doing addition, which is nothing but a linear combination of quantum states. Quantum states. About what quantum state? Related to your quantum particle. So your quantum particle can exist in multiple quantum states. So if you want to define your quantum particle, you need to add all its quantum states. Okay. For a single qubit, how many quantum states are possible? State 0 and state 1, basis state. So these two are called basis state. State 0 and state 1 are called basis state. So if you have pen and paper, please note down. Okay, fine. So apply theta equal to 0 in this example. Apply theta equal to 0. So apply for theta 0. You'll get cos 0 by 2, sin 0 by 2 multiplied with state 0 multiplied with state 1. Okay. So interestingly, you can see the second angle. So this psi is called second angle. Second angle. Okay. Which is representing the exponential form with the imaginary. So this is in the form of e to the power I multiplied with your second angle. Now we are focusing only on first angle. Okay. So recall from the previous slide. What is the meaning of theta? Theta is the angle between your z-axis to quantum state vector. Quantum state vector. Okay. If theta equal to 0, it will point to north pole. So your quantum particle will point to north pole. So this is the understanding about this slide. When you apply theta equal to 0, what you will get? When you apply theta equal to 0, what you will get? When you apply data equal to 0, what you will get? When you apply data equal to 0, what you will get? Anybody able to answer?
Just
Am I
the unit
audible? Are you
vector.
able to?
Just the
Yes,
unit
sir. Tell
vector
me,
in
sir.
the x-axis.
Exactly, sir. So it will represent, sorry about that, it will represent z-axis. So look at here. For reference, I will show. If data equal to 0, the quantum state vector move to z-axis. It will point to north pole, not in x-axis. So please look carefully. Okay, if data equal to 0, okay, cos 0 by 2 is 1. 1 multiplied with state 0, you will get state 0. Plus sine 0 by 2, you will get 0, 0 into state 1. So everything is get eliminated. You will get only state 0. So which is nothing but, it is an identity gate. It is an identity gate. If you apply data equal to 0, it will do nothing. It will do nothing. The state remains same. The quantum state will remain same as it is. So is it clear, sir? Is it clear? Kumaroil, sir?
Yes, 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 yes.
Thank you. Thank you. Okay. So this is nothing but your classical gate. Classically, we can do identity gate. If you apply identity gate, it will do nothing. The state remains same. The data remains same. Okay. In same way, if you apply data equal to pi, what happens? So apply data equal to pi and tell the answer. Cos pi by 2 multiplied with state 0, sin pi by 2 multiplied with state 1. Put in the chat box. If data equal to pi, what will happen?
Negative unit vector in the z-axis.
Exactly, sir. Z-axis only, but we need to be little particular. It will go to state 1. If data equal to pi, what happens? Visually, you can see it will do pi rotations. It will do pi rotations over your x-axis. It means the quantum particle will come from state 0 to state 1. From state 0 to state 1. So this is nothing but NOT gate operation. So classically, what is the meaning of NOT gate? What is the meaning of NOT gate? If you are giving 0, it will convert into 1. Okay. Suppose if you are giving 1, it will convert into 0. So it is a bit flip. It is a bit flip. In quantum, it is a state flip. It is a state flip. So exactly 0 to 1, 1 to 0, opposite state. Opposite state of pi rotations. Okay. If data equal to 0, if data equal to 0, identity gate. If data equal to pi, NOT gate. Okay, we covered 2 classical gates. So nothing very big difference between quantum and classical so far. Okay. Next, the trick is if you apply deta equal to pi by 2. Deta equal to pi by 2. Now applying this formula and tell me where it goes. So 0 means north pole, pi means south pole, pi by 2 means where it will. So look carefully. Look carefully. Deta equal to pi by 2. Sudhir Ranjan sir, if you apply deta equal to pi by 2, where it will go? Kumaravil sir, are you able to guess?
I'm not calculating very particular, but in between the, this,
Exactly, sir. In between
yeah, in
state 0 and
between,
state 1.
yeah, that's right.
So it will go to equator. It will go to equator. So 0 means north pole. Okay. Pi means south pole. Pi by 2 means exactly in between. So this is nothing but it will create equal superposition. So what is the meaning of superposition? Both state 0, okay, and state 1 will exist at the same time. So this is 50% away from state 0. Okay. Also 50% away from state 1. So this is the meaning of equal superposition. It will go to x-axis. It will go to x-axis. Okay. So very good. So that is why you can see both components are there. Both cos component is there, sine component is there. If you take it out, 1 over root 2 multiplied with state 0 plus state 1. This operation is called Hadamard gate. Hadamard gate. So this will create equal superposition, not only equal superposition, it will create randomness. It will create randomness in your qubit. So what is the meaning of randomness? If you try to measure your qubit, in superposition, it means you will have value 0 for 50% of time. You will get binary value 1 for 50% of time. For 50% of time. It means you will get a random value. So nobody in this world able to predict what value it will generate in next iteration. Suppose if you are interested in pure random number generation, you need to use Hadamard gate. Okay, equal superposition. Okay. Now we try to do little modification in second angle. Look at the second angle, psi equal to pi by 2. If you apply psi equal to pi by 2, it will do rotation from x-axis to your y-axis. So both this point and this point are equal superposition because it is in equator. So wherever if you are dealing with your equator, each and every point over your equator is equal superposition. So whether it is in x-axis or minus x-axis or y-axis or minus y-axis, everything is equal superposition. Because we are changing something with our second angle, which is involved with the random number, okay, you can see one component is added, I is added with your state 1. So it will include pi by 2 rotation in your phase, pi by 2 rotation in your phase. Okay. So we covered state equal to 0 means north pole. Okay. State equal to deta equal to pi means south pole. Okay. Pi by 2 means x-axis. Okay. Pi by 2 along with the second angle pi by 2 means phase shift in your signal. So recall all these steps. Okay, recall all these gates. So this gate is called phase gate. This gate is called pi by 2 phase gate, which is equal to S gate, which is equal to S gate. So what S gate will do? It will introduce pi by 2 rotation, pi by 2 rotation in global phase, in global phase. So this psi is called global phase. This psi is called global phase. So if you have pen and paper, please note it down. Next, what we are doing, we try to recall what are the operation we did so far. So we have z-axis. Z-axis is called, sorry about that. Z-axis is called computational basis. Computational basis. Okay. X-axis is called real axis. So x-axis contains real components. Real components, or you can say real values. Real values. Okay. So I try to change color. Try to change color. Yellow is not visible. I try to use violet. So this y-axis is called imaginary axis. So whenever if you have any imaginary value, it will represent in your y-axis. Okay. So positive x denoted with positive state. Okay. Negative x denoted with negative state. In the similar way, you can represent y as positive y minus y as negative y. So completely we have three pairs now. So state 0, state 1. Okay. Positive, negative. Positive y, negative y. Okay. So this is for z axis. This is for x axis. This is for y axis. So once you have three pairs, you can represent your quantum particle anywhere in this block speed. Anywhere in this block speed. Okay, remember all this stuff. If you want to represent your quantum state in matrix form, so this is your quantum state, this is your matrix form. This is not 4, this is matrix. So imagine like this, 1, 0. So why state 0 is represented as 1, 0? Because the northern hemisphere related to state 0. So northern hemisphere related to state 0. So imagine like this. So this is your upper component. This is your lower component. So upper component denotes northern hemisphere. Okay. Lower component denotes southern hemisphere. Okay. Because state 0 is mapped to northern hemisphere, the upper component is 1. So where state 0 exists in your block sphere? In northern hemisphere. That is why the upper component is 1. If you understand this, you can understand state 1, which is in lower component, southern hemisphere. So each and every matrix in quantum, okay, have some physical intuition. So if we understand physically, we can easily represent in mathematical form. Okay. Same way, if you go for positive state, it is in equator. It is in equator. So equator related to state 0 as well as state 1. That is why both components are there. Both the upper component is 1 and lower component is 1. And what is the amplitude? 1 over root 2. So this is called a constant factor. You can say constant factor, or you can say amplitude. Okay. So if you want to represent the minus x-axis, you can represent with minus state. The second component is minus 1 because it is in opposite side. Because it is in opposite side. So each and every matrix in quantum has some physical intuition. Okay. In same way, you can represent I, y-axis, the second component as I, and minus I as minus I in the second component or lower component. So totally what you can do, you can visualize your quantum gates. So all these matrices are called quantum gates. Okay, you can visualize in this way. So this is the link. If you want to use or work, I'll share this link with you. So if you have a laptop or system, please go to here. So click this link. Click this link where you can see block sphere. Where you can see block sphere. Okay. So these two are pure states. These two are pure states. State 0 and state 1. So these two are called pure states. These two are pure states. Okay. If you want to create qubit, if you want to create qubit, if you are creating qubit, creating a qubit, okay, there is only two possibility. Either you can prepare in state 0 or in state 1. Okay. So why we are able to only create in state 0 or state 1? Because we are representing binary value. We are representing binary value. Okay. So these two are called known state to us. So for humans, only binary value or known value. Okay, we are converting all our data into binary value. We try to map this binary value to quantum bits. So click state 0, click X gate. What happens? Anybody able to follow? So go to this link, click stage 0, click X gate and observe what happens. So I'll represent in this way, stage 0, then I am applying X gate, where it goes. Click stage 0, click X gate. Okay, observe where it goes. Are you able to follow? Are you able to work out? Hello, am I audible? Are you able to work out? Click stage 0, click X gate and observe where it goes. Okay, okay, very good. I will explain. So all of you go to this link. I already shared in this link. Okay, so observe what I am doing. So click stage 0, click state 1. These two are called pure states. So these two are called pure states. pure states. Okay, stage 0 and stage 1. So what I am telling, click stage 0, click stage 0, then click X gate. So this is your X gate. Click stage 0, above 1, then click X gate and tell me where it goes in your block sphere. Where it goes. Are you able to see where it goes? So without your response,
Get
very
one.
difficult to proceed. Yes, sir. Kate one. Exactly. Exactly, Kate one. Thank you. So it means clicking stage 0, clicking X, it will move to state 1. So I will write mathematically stage 0. Once you apply X, it will move to state 1. It means it is a not operation. Not operation. Okay. So from cat 1, again, if you are applying X, it will move to stage 0. So check this. Check this. So click stage 0, click X, it will go to state 1. From state 1, if you click X, it will go back to stage 0. So applying 2X gate will cancel each other next to next. Applying 2X gate will cancel each other next to next. Okay. So next what we try to do, we click Y gate. We click Y gate from stage 0. So from stage 0, apply Y gate and observe where it goes. It will go to state 1. It will go to state 1. Check here. So click stage 0, click Y gate. It will go to state 1. But if you carefully observe, it will lead to pi by 2 phase rotation. Pi by 2 phase rotation. So physically you cannot see this rotation, but downside you can able to observe this phase disk. So this will add plus pi by 2 phase rotation. Okay. So what you can conclude, X gate is not gate. X gate is not gate. Y gate also not gate, along with pi by 2 rotation in phase. So Y gate have more computation, more expression, more freedom to operate your signal. So imagine NOT gate only have bit flip, but Y gate also do bit flip along with phase flip about 2 pi by 2 rotations. Okay. What we'll do? We'll do stage 0. From stage 0, apply Y. It will go to state 1. State 1 plus pi by 2 rotations. Okay. From here, if you again click Y, it will go back to stage 0. It will go back to stage 0. So do this. Do this. Now we are in stage 0. Click stage 0. Click Y gate. You can see bit flip along with phase flip pi by 2. Again, over here, click Y gate. It will go back to stage 0. So apply 2Y gate will cancel each other effects. Apply Y gate next to next. Okay. It will cancel each other. So click stage 0. Click stage 0. Okay. Try to click Z gate and tell me what happens. So click stage 0. Apply Z gate. What happens? Are you able to follow? Click stage 0. Click Z gate from there. Observe what happens. Anybody able to do? Already we are running out of time.
More change, sir.
It will do nothing. Yes, sir. It will do nothing. It will stay in stage 0. So Z gate will act like identity gate in stage 0. So Z gate will act like identity gate in stage 0. Stage 0. Okay. So what we'll do? Click state 1. Click state 1. Okay. Apply Z gate and observe where it goes. Apply Z gate over state 1 and tell me where it goes.
State 1.
State 1. Very good. But look at here. Look at here.
5.
It will do rotation pi. It will do rotation over pi value. So
Yes,
Z gate will do minus sign. Will introduce minus sign for your state 1. So Z gate will do a sign change. A sign change. Okay. In stage 0, it will act like identity gate. Will act like identity gate. Okay. So only in stage 0, it will do nothing. Only in stage 0, it will do nothing. Every point in your block sphere, it will introduce sign change. So remember this. So all these things will help you if you want to create a quantum gate, quantum circuit. So click stage 0, apply Hadamard gate, H gate. It will introduce equal superposition. It will introduce equal superposition. It will go to equator in x-axis. So in positive state. So how to understand this? How to understand this? So click stage 0, apply Hadamard gate. It will create equal superposition. It will go to positive state. So positive state is nothing but x-axis. Okay. So click positive state, apply Hadamard. It will go back to stage 0. Now we are in positive state. I try to apply Hadamard gate. Observe what happens. It went back to stage 0. So applying two Hadamard gate next to next will cancel each other. Apply two Hadamard gate next to next will cancel each other. Okay. So these gates we discussed. The next gate is about S gate. So click yes in stage 0 and tell me where it goes. Click stage 0, apply S gate and tell me where it goes. Are you able to follow? So please put in chat box or unmute yourself and answer. Are you able to follow me? Yeah, I'll send that link. No issue. Once you are following, if you are able to follow my track, you able to understand the gates easily. So that is why I'm asking to do by yourself. So click stage 0, click stage 0, click yes gate and observe what happens. It will do nothing. So it will do nothing. It will retain in the same state. So just like Z gate. Okay. But click state 1, apply S gate, and observe what happens. Click state 1. Okay. Apply S gate. It will introduce 5 by 2 rotation. So what happens? It will introduce 5 by 2 rotation in XY plane, along Z axis, So it will do pi by 2 rotations. Okay. Compare Z gate with S gate. What Z gate will do? It will do pi rotations. What S gate will do? It will do pi by 2 rotations. So that is why sign is never changed, because it is in between. So this is positive side, the opposite is negative side. It will come exactly to Y axis. It will come exactly to Y axis. Okay. To understand that, click 0, apply Hadamard gate, then apply S gate. So I will write in equation. Okay. Click stage 0, apply Hadamard gate. It will come to positive state. From positive, again, if you are applying S gate, it will come to Y axis, I gate, I state. So starting from here, it will come one, it will come over here. So this is rotation 1. Okay. From positive state, if you are applying S gate, it will go to I state. This is operation. Okay. So if you understand this, click stage 0, Okay. What we are doing, we are applying Hadamard gate. It will come to positive state. From positive state, if you apply T gate, where it will go? So follow this instruction. Click stage 0, click H gate. Okay. It will come to positive. From positive, if you apply T gate, what happens? From positive, if you apply T gate, what happens? It will go to in between positive state and I state. So I will show you. So click 0, click Hadamat. Okay, click T gate. It will go in between your positive state and this I state. So it will introduce 5 by 4 rotations in your phase, in your signal phase. Okay, so Z gate 5 rotation. Okay, it will change sign. Okay, what S gate will do? It will do pi by 2 rotation. What T gate will do? It will do pi by 4 rotations. So note down this. Okay, so we try to build all these gates in the composer. So this is the IBM Qiskit composer. So you can see 4 quantum bits over here. So Q0, Q1, Q2, all these are quantum bits. Okay. So you can see downside C4. This is called classical bit. This is called classical bit. So totally we have 4 quantum bit. We have 4 classical bit. So that is why represented over here. Okay. For simplicity, what we can do, we try to delete quantum bits. So click Q1, select this bin button, delete qubit. Okay. So click Q1, select bin button. Click Q1, select bin button. Click C4, select minus. Click C3, select minus. Click C2, select minus. So we created only one qubit and one classical bit. One classical bit. So do like this. Go to this composer. I already shared this link with you. So once again, I will share with you. So go to this link. Go to this link. So it will lead to this web page. Okay. Try to delete 3 qubits. Try to delete 3 classical bits for simplicity. For simplicity. Okay. We try to do the first gate. The first gate. Always qubit is starting with state 0. So this is pure state. This is pure state. Okay. So look at this wire. Look at this wire. It is like electrical wire. Stage 0 means off. Stage 0 means off. Some children try to mute. Okay. Thank you. Okay. Over here. So stage 0 means it is representing off state. Off state means no power supply over here. So consider this is like electrical wire. Now power supply is not there. Now power supply is not. Okay. So all the qubit initialize to stage 0 by default. So look at down. Look at down. This is your probability. So for 0, probability is 100% because it is in stage 0 initial condition. Okay. Look at the state vector. Move your mouse over here for stage 0. The signal strength is full. Amplitude is exactly 1.0. It means full signal strength for stage 0. Okay. So look at your Q sphere. It is pointing to northern hemisphere. North pole. Exactly north. Okay. So this is for stage 0. Okay. If you are implementing NOT gate, this is your NOT gate. So look over here. The second gate is called NOT gate. The second gate is called NOT gate. Okay. So drag and drop, not getting Q0. Drag and drop, not getting Q0. So what happens? Initially stage 0. Okay. Now you applied NOT gate. Because of NOT gate, it will turn into state 1. State 1 means it is on state. It is in on state. So power supply will be there. So power supply will flow in this wire, electrical wire. So that is why everything is changed. Now the probability is moved to 1. Okay. Amplitude moved to 1. Okay. Here you can see the bit flip, state flip. So from North Pole, it is pointing to South Pole. So imagine in this way. Imagine in this way. Okay. What we are doing, again we are implementing one more NOT gate over here. So try to drag and drop one more NOT gate. Try to understand your circuit. We started with stage 0. We applied NOT gate 1. Okay. After NOT gate 1, it will turn into state 1. We applied NOT gate 2. Again, it will convert into stage 0. So stage 0 means no power supply. So it is pointing to 0. state vector signal strength pointing to 0. Where 0 is mapped? 0 is mapped to North Pole. Okay. So what do you do? Drag and drop one more NOT gate. Try to understand what happens. Again, it will do a bit flip. So state 0 is converted into state 1. Again, everything is changed. Everything is changed. Okay. So to delete all these gate, what you do? Click this gate, press delete button. Click one more NOT gate, press delete button. Click one more NOT gate, press delete button. Now your circuit become empty. Now your circuit become empty. Okay. So next what we do? We try to implement a Hadamard gate, H gate. So look over here. This is called your Hadamard gate, H gate. H gate. Okay, first gate. So what H gate will do? It will create equal superposition. Equal superposition. Okay. So what is the meaning of equal superposition? One position over another position at the same time. So look at your Q sphere. It is pointing to both North Pole as well as South Pole simultaneously. So this is an example for equal superposition. For understanding what I do, I try to enable only the Q sphere. I disable graphical editor, go to panel, go to view, go to panel, disable code editor, go to view, panel, disable state vector, go to view, go to panel, disable probability, only Q sphere is there. So if you are implementing Hadamard gate, what happens? If you're implementing Hadamard gate, what happens? It will create equal superposition. It will create equal superposition. Simultaneously, it will point to North Pole as well as South Pole. So enable all these panels again. Enable all these panels again. Okay. So this is graphically what you are seeing. By coding wise, you are able to enable over here. I try to minimize all these window. So you can reconfigure your panel in this way. Okay. You can reconfigure. So move your mouse in this way. So here you can see OpenQuasm. OpenQuasm stands for Open Quantum Assembly Language. OpenQuasm stands for Open Quantum Assembly Language. Okay. So click here, select WizKit, select WizKit. WizKit stands for Quantum Information Science Toolkit. So I try to vary color for easier understanding. WizKit, Quantum Information Science Toolkit. So this is a platform developed by IBM where you can be able to simulate as well as using real quantum system for 10 minutes. 10 minutes they are giving access for you. Okay. So each and every minute it will cost nearly 9,000 rupees. So nearly they are offering 90,000 rupees of quantum processor access free for. So this is more than enough if you want to do PhD. Okay. So this is the equivalent Python code for your quantum circuit. Okay. So try to select this gate, press delete button. Now you can change in your code. Try to import a NOT gate. Now you try to see the change in your code. So try to implement Hadamard gate. Again, you can see changes in your code. So in this way, you can easily understand this QuizKit platform with the help of compose. So this is at beginner level. For beginner level, this much is more than enough for you. So click this daily. Click this daily. Okay. So click state 1. Click state 1 by enabling NOT gate. So this is stage 0. Okay. This is NOT gate. Now it is turned into state 1. Now what do you do? Try to implement Hadamard gate and look what happens. You can see some color change, red color. It indicates, it will denote negative state. So look at here. Look at here. Click 0. Click 0. I'll try to write. Click 0. Apply Hadamard gate. Okay. It will go to positive state. Okay. The second option, if you are in state 1, if you are applying Hadamard gate, it will apply Hadamard gate. It will go to negative state. So this negative state indicated by red color change. Red color change. Because it is in negative side of this sphere. Negative side. So I tried to erase all this stuff. I tried to repeat what I say. Click state 0. Apply Hadamard. It will come to positive. Okay. Click state 1. Apply Hadamard. It will come to negative side. This negative side indicated over here with the help of a color change. With the help of a color change. So likewise, you can explore this tool more and more. There are so many tutorials for IBM Qiskit circuit. There are so many tutorials for Qiskit circuit. So come over here, you can click tutorials. So many tutorials they gave. Okay. If you go for documentation, they will have so many documentation, right? If you want gate, they will give gate. So circuit and operators. So today's lecture, we covered only the fractional part of this circuit. And we discussed only the fractional part. So I'll share this link with you. In your free time, please go and explore how to construct a quantum circuit. So you can download this Jupyter notebook over here. It is a Python notebook. You can upload in Google Colab or you can upload in Jupyter notebook. You can run this circuit, whatever you want. So initially, use this composer for easier understanding. Once you mastered, you can go for full-fledged coding like this. So within this, I try to stop my lecture. If you have any doubts, you can ask.
Participants can unmute and speak. Is it the thing we have muted? So you can unmute and speak. I hope that option is available, or you can post your doubts in the chat box.
Thank you, sir. How to generate a random gate?
Random gate, this one, sir.
Yeah, because I want
Suppose,
everything is
yes.
performed is deterministically.
This
But
one is
we introduce the word
this
random.
one is random. Yes, this one is random. Are you able to see the screen? Once you implemented Hadamard gate, it will generate either 0 or 1 randomly. So how to conclude the randomness? Try to do measurement. Once you do measurement, superposition state will get collapsed. You will get either one of the value. So in this case, you got 0. In some other case, you will get 1. So more you run this code, more you will get different output. Very good question. So this circuit is example for true randomness.
True random. Okay.
True randomness.
Yeah,
Because
yeah.
nobody in this world able to predict what it will generate in next sequence.
But anyway, we get
If
an
you want to
output,
generate a
no,
random
through,
number,
yeah. It
yes,
may be
yes, yes,
pseudo random.
through
Yeah,
measurement.
that's it.
This is not pseudo random, sir. This is random.
Uh,
This is random.
no, the calculation,
You
the
are from
linear
computer
combination.
science?
Yes, yes.
You are from computer science
So,
or
yeah,
physics?
inside this Hilbert space, everything is
Okay,
deterministic and the true randomness,
exactly,
yeah, won't exist. But for the sake of what
exactly,
do you
sir.
call
But
practical sake, we call it random.
no, no.
That's what
See,
my
suppose if
feeling.
you have a quantum particle. Okay, okay. Suppose if you have an electron, okay. Suppose if you are creating superposition for that electron, it will go in the equator. But once you do measurement, you are doing physical action over that electron. Either it will go to 0, either it will go to 1 randomly, because randomness is intrinsic property of quantum particle. So only in classical we say pseudo random, but in quantum it is always random. So I can believe this. Once you do measurement, superposition state will get collapsed. It will either go to 0, either go to 1, based upon 50-50 probability, but not exactly 50-50, sometimes 52-48, sometimes 25-75. Anyway, it will go. The more you run, the more equally you will get probability.
So in that case, what is the seed of that random?
There is no seed, sir. That is the interesting point, because we are
Yeah.
dealing with real object, quantum object. Very good question.
No, this,
Only for
no.
classical, we are generating seed value. Only
Hmm.
for classical, we are generating seed value. Based upon the seed value, you can generate number. Okay, because it is not a true random. It is based upon some seed value. But in quantum,
Yeah,
there is
that's
no
right.
seed value.
In quantum, there is no seed
Yeah,
value. I agree. But
no
in
seed
order
value.
to write,
Yes,
yeah, that's right. Theoretically, yeah. In order to implement that, we need, for example, we are just based on the spherical coordinates. We we
yes.
actually perform the calculation, three-dimensional calculation.
Theoretically also, sir.
Yeah,
Theoretically
yeah,
also, you cannot say
uh,
where it goes.
uh,
For name's sake, you cannot say where it goes. Randomness you
that's
cannot produce in mathematics.
yeah.
Just like
Even
theoretical
even
case you can
mathematics
do.
cannot produce. Yeah, that's right. Yeah.
Even mathematics cannot describe randomness. Exactly, sir.
That's right.
Very good question.
So,
Very good question.
so I wonder how this QASM, the assembly language, hiding the seed.
Okay.
That's
No,
my
no,
feeling.
no,
That's
no. It is not hiding seed. Okay, okay, okay. What happens? This assembly language will translate any quantum language into any quantum vendor. Suppose if you are doing in IBM, okay. So this is the code version for IBM. You can use the same code. You can use the same code. You can convert into OpenQuasm. You can run on Google Quantum also. You can run on Microsoft Quantum also. So whatever you are doing, it will do for another quantum particle in another quantum configuration. So here we are using electron. Here we are using electron. In Microsoft, we are using topological qubit. So accordingly, this code will translate according to the hardware architecture. That is the beauty.
Hmm. Thank you, sir. Thank you.
Thank you, sir. Thank you. Very good. Suppose if you have any doubts, you can put question for me. Okay, I'll share my social media ID. So I'll post whatever the quantum related events happening across India. I'll post very frequently. Thank you all.
Thank you so much, sir, for your insightful and engaging session. It was truly useful and gave us a deeper understanding of a topic. Thank you once again, sir.
Sir,
Thank you, ma'am.
Jayakumar, sir, there is one doubt posted in the chat box whether Qiskit is free or not, whether it's an open source.
Quizzkit is Quizzkit is free. It is open source. They require your credit card for verification purpose because they are giving quantum hardware access. Only for that they are asking credit card information.
So that was a
So
doubt
if you are
posted,
not
and
using quantum,
thank you, sir.
yes. Thank you, ma'am.
Yes, sir,
Thank
please
you. Thank you.
proceed, sir.
Suppose if you don't want to use that quantum hardware, don't give credit card information. Okay, because I will not guarantee they will take your money if in case if you're accessing more than 10 minutes time. Okay, so stay for Jupyter notebook. You can stay with your Jupyter notebook or Google Colab. So you can do simulation. So whatever I'm doing over here, it is kind of simulation. We are not accessing real quantum hardware. Okay, this is my suggestion. For the beginner, no need to use actual quantum computer. So theoretical research is more than enough.
Thank you so much, sir, for taking the
Thank you,
basics
ma'am.
of what is quantum computing. And since most of our participants are new to this topic, I hope this is very beneficial for all of you. And thanks once again, sir, for accepting our invite. Every time you are ready to help us and support all the faculty members who come to you for any support regarding the quantum computing technical doubts as well as taking the sessions. We wish to collaborate with you again, sir, in the upcoming sessions or for any collaborative projects. Thanks from our management and from our faculty coordinator team of this FDP. And from the participants, I extend my sincere gratitude to our resource person, Dr. Jayakumar, sir, for spending his precious time with us. Thank you, sir. Thank you once again. And to
Thank
the
you, ma'am. Thank you all. Thank you.
participants, yes. And to the participants, we will be sharing the feedback link and the attendance link only after an hour because so that you can jointly give the attendance for both the sessions in one link. Okay. The feedback link also will be shared in an hour, so please be patient. And you can take a 5-minute break so that the second resource person will be joining us soon. Please wait for 5 minutes. You can take a small break and join us. In the same link, this link, this meeting will be going on. Thank you.
Okay.
Just information to the participants, the feedback link and attendance link will be shared after some time. Please be patient. So welcome, sir. Good evening.
Yeah, good evening, ma'am. Good evening also. Am I audible?
Yes, yes, the voice is very clear. Can we
Yeah,
try
yeah,
that
I'm audible. I'm able
slide?
to hear
Yeah.
you. Yeah.
Sir, I have made you a presenter now.
Okay, ma'am. So I'm sharing the slide.
Yes, yes.
Let me know like your.
Yes, sir. Sure, sir. Sure, sir.
Yeah.
Yes, sir. It
So
is
is it
clear, sir.
visible?
Yes, sir. Yes, sir. So a warm welcome to Dr. Shashikant Pandey, sir, the senior scientist from the Society for Electronic Transactions and Security, Chennai, India, to our second day of our FDP on quantum computing and quantum machine learning solutions for sustainable future. Sir, we are indeed, it is a pleasure to have you amongst us today as a guest speaker. Let me give a brief introduction about sir. Dr. Shashikant Pandey is working in SETS as a scientist and has received his PhD from the Department of Mathematics, University of Delhi. He has completed Master of Science Mathematics from Banaras Hindu University, Varanasi. His research focus on Boolean functions and more specifically on the cryptographic and combinatorial characterization of Boolean functions. Some of the other verticals of his research are post-quantum cryptography, privacy preserving technology and formal methods. So it's a pleasure to have you with us today and over to you, sir.
Yeah. Thank you, ma'am. Thank you for this nice introduction. So I'm audible. That's fine. It's going on.
Yes, sir, it is very clear.
Yeah. Yeah. So uh, what here I'm going to give the details about in next 1 hour is about how we go towards the core part of the most of the security solutions. Either it is developed by quantum phenomena or it is developed by classical phenomena, like how you the both phenomena is basically a source of the randomness, and the achievement of this randomness is required to build the almost all secure systems and their usability. So what I would cover is mostly on how we perceive the idea of the randomness in terms of mathematical as well as algorithmic sense. And another thing I would like to cover is how we test those randomness in the given binaries, or you can say the given sequence, because this is another area of work where we are also working, like how to verify that the given sequence is satisfying all those standards required to say that okay, so this is uniformly distributed, or it is called as a random sequence. So these two set of problem is majorly which I'm going to cover in next couple of hours. So that is the idea basically, that what how we perceive, because I can say like the meaning of randomness is very vast. So and it totally depend on the context in which it is telling. So if we are talking in terms of sequence, then you better understand that what I'm going to say in terms of the randomness. Similarly, the test suites are also in terms of the context of the cybersecurity. So mostly the test suites, what I'm going to cover is specifically designed to verify the randomness of those sequence which are mostly in use or use case for the cybersecurity solutions, like wherever the requirement of random sequence is there. So there we will apply those test suites to verify that whether whatever the I generated is satisfying the randomness condition or not. So as I told, like the meaning of randomness is like completely depend on the context and how we perceive the idea of the randomness. It depends on the what type of object for which we are talking about the nature, like what nature we are talking and which nature we are looking that to make a pattern or trace some footprints, and based on that we are able to say that okay, somehow I'm able to get some patterns, and that's why the meaning of the actual core idea of the randomness is violating. So this, but the need of the randomness is very much required, like because without uh, uh, the trust or mm, the source from where you can say that okay, it is we are that much percentage we are trusting that it is giving a random sequence, and based on that random sequence we club the other physical systems, and later on build on top of these two things, we build the uh, uh, whole physical system for the security. But ultimately the proof of the security, or you can say the confidence of the security, is coming from the particular source from where we are receiving the actual random sequences. So it is just a merger of source where the actual random phenomena is happening, and on top of that the technology or some realistic or physical system which is combining these two things and giving us beautiful solutions, which is said to be secure because of that the nature of that source. So these are some uh, well-known statements about the meaning of randomness, how they defined. So you can see that the uh, third point where it is telling like a sequence is random if there is no rule or law that can be used to produce it. So that is a common perception, like if we talk in terms of the sequence, then it should be like that, like there should be no rule or law. Then if there is some law or there is some rule, then it can't be random. But continuing this same idea, we can ask a simple question like how to find out those rules or law. If we have those sequence, then how to find those rules in law, and how to say that no rule or law will exist to define that pattern. So these two questions are uh, completely a cyclic structure, and based on that, all those uh, the testing as well as the generation of the random sequence is going on. So I will just tell about these three people work, Chaitin, Kolmogorov, and Solomon. So their theory, they worked basically mostly on the defining the randomness, or you can say the meaning of randomness in terms of the length of the program to generate the sequence. Because ultimately I told the previous line is just telling about that if no rule and law, then I can tell that it is random. But the meaning of the rules and law is basically lies under the logic from which you are able to generating one sequence. So the question is that how to build a logic to generate a sequence. And next question is that how to build a logic to say that this sequence have no any logic or no any rule. So both of things are, that's why I'm telling like a cyclic situations, and based on that the meaning of randomness has been defined. To explain it more clearly, I'm just giving one example, like to grasp the idea of that C case. I'm just planning to give one example of sequence, like in that case, how one can perceive the meaning of randomness. So since I told like, okay, so if sequence is not satisfying any rules or law, then I can say that it is a random. But practically, if you see, this is a sequence. So if I can ask like, okay, so what can you say about that sequence, and related to the related to finding the patterns in that sequence. So in that case, you can easily observe. I think if some of you can tell, then you can easily find out that how it is going on. It is just a repetition of 1 0 1 0 1 0 12 times. So this is the case. Based on the observation, you can tell, okay, the sequence have a pattern, and I can easily find a law which can define the bits of that sequence. So this is the way to see that how to find out a pattern. So logically, it will come in terms of the decision of the or the observation of each bits, and then relate with the previous observed bit, and based on that find out that, oh, this pattern is going on, whatever I observed. Based on that, I am able to write the next one. So I can say that, okay, this is satisfying a pattern. So this is the way to tell the sequence to be uh, not a random or satisfying condition. The second case is this S2. So here the sequence is going out to be 1 1 0 1 1 0 0 1 1 0 1 0 0 1 1 0. So if you observe it, and based on that observation, if someone is asking like, okay, what type of logic I can build so that I'm able to generate all binaries or all bits in that sequence. So it looks like, I don't know, like, are you able to give any logic for that in couple of minutes, like what you have done earlier in S1? So naturally, to find out the logic is a difficult problem. It is not that easy, like based on the sequence itself, you are able to tell, okay, this set of lines or set of rules, if I define, then I'm able to say that if you follow these set of rules, then I'm able to generate all binaries of that sequence. So come to the generalized case of the same idea. Like here, since in case of 24 bits, I'm not able to define a rule or law, then what should be the general perspective to see those binary sequence for checking off randomness or checking off any patterns available in those sequence? So this problem has been looked quite differently throughout the last, I can say, like 200 decades. Uh, like in starting from 1960, where the CKS idea has been proposed to see those complexity to defining those logic to build a sequence. It has been widely studied and find out that how to look this problem to define the meaning of randomness and to build a set of rules to test them. So if we talk about the finite size means fixed size sequence, then in that case, we have fixed number of sequence also. So there is interesting difference between a finite sequence and infinite sequence. So, but mostly since we are talking about cybersecurity perspective, so we so this system should be finite, like it will not generate an infinite sequence, so that the basic building block of the generation of cyber secure physical system or uh, algorithm is based on the finite length sequence, because always it is required to be a finite size of key, finite size of message, as well as finite size of ciphertext. So mostly it is lying inside the uh, finite set of uh, finite set of sequence which have a fixed length. So here we are moving towards this problem to see the testing of the sequence which are finite length. So in case of the same approach, what CKS has been proposed, like how to compare a given sequence with a set of rule you fix to generate that sequence. So if I talk about like for 3-bit sequence, so you can easily find out that total 8 type of sequence are possible. That is displayed here in the set S. So now for all these elements of 3-bit sequence, we are going to find out the rule or logic. Based on that, we are able to generate those binaries. So following are the procedure. Like if I want to see the binary sequence which is 111, then I find out the pattern like, oh, 3 ones are there. So it means logic is write 1 3 times. You are able to generate this binary sequence. Same pattern is there in case of 0 0 0. 3 zeros are there. So I can tell like these two sequence can be defined by just one set of one line, which is called program or logic or whatever in your understandable words you can choose it. But ultimately, only one set of rule is required to define 111 and 000. So I can tell that there is length 1 program which can generate this 111 and generate 000. Similarly, if I go to the length 2 program sequence, so here this 001 is a sequence which required 2 steps. First, you write 0 twice and then write 1. So these 2 steps or these 2 set of rules is there to define these binaries of length 3. Similarly, if I'll go for 110, then these 2 steps is there to define that sequence of 3 bits 110. Write 1 twice and write 0. So in this way, ultimately you are able to define 1, 2, 3, and 4 binary sequence and their corresponding length of steps. The same is applicable in case of 011 and 100, like what we have done here. Step 1 is write 0, step 2 is write twice 1. So if we go to the statistics that how much the length of the program to write those sequence, then here 4 programs of length 4. Now, ultimately for 6 binaries, we have achieved. 4 is here, 2 is here, 6 are completed. The remaining is 2 sequence, which is 010 and 101. So if you see 010, then it has to be defined in 3 set of rules. Step 1 is write 0, step 2 is write 1, step 3 is write 0. So you whatever the previous choice you have done, using the same choice, you need 3 steps to define 010. Similarly, 101 is required to be 3 steps. So these 2 sequence actually required 3 steps. Top 2 sequence 011 and 100 required 2 steps. These 2 required 2 steps, and finally only 2 sequence required 1 step. So ultimately you are able to find out the set of rules, length of rules corresponding to the all possible 3-bit sequence. So what is the meaning? So meaning is that if the length of the steps and the length of the binaries are equal, then it is said to be more complex. Or you can say that to define them, I need to go till that much step, which is equal to the length of the sequence. So ultimately, the behavior of randomness is connected with the behavior of the complexity to define those rules which generate those sequence. Because I already told, like, there is no rule. If there is no rule to define that sequence, then we are not able to decide that it is random or not. So in the reverse of that, we have to prove that, okay, there is no rule. So it means we have to fix the rule to define those sequence, and whatever the method we are doing to fix those rules, so we will look inside the difficulty of those methods, like how we are um, defining those rules to generate those sequence. So somehow here difficulty is related to the length of those steps. So since the length of the steps is 3 and the length of the sequence is 3, so in that case I can tell that these two binaries are more complex rather than the remaining 6 binaries. So this is one of the way to see the CK's work in case of the defining the randomness. So the next question is that, what if n increase here? Here we have taken n is 3, so 3-bit sequence we have chosen, and in that case we define like how to justify the complexity of logic to define the sequence. The next case is that when n is going to be 5. So this I will not explain in details, but you can do by yourself on pen and paper and see that how the results are coming and how the results are going towards the complex situations. So similarly, n equal to 4 you can try, n equal to 5 you can try. So for n equal to 5, like out of 32 sequence, there are 32 possibilities of those 5-bit sequence. So 1 out of 16 can be described by less complex program. It means if you multiply, it means 2 out of 32 can be defined by only less complex program. Remaining is required to be more complex, or you can say the length of the steps are almost more than 1, 2, 3, 4, like that. But how many of them is required? 5 length steps that you need to explore. And when you do the pen on paper, then you realize it. Yeah, so as I shown you the example of a sequence earlier in my first slide, this S2. So this is looking like this. By seeing that, you're not able to find out that what logic satisfy. But by seeing that, you can't tell that, oh, no logic will satisfy this, because here is the case. So this is the set of rules. Just 2-line rules are there. Based on that, we are able to define the particular sequence. First rule is define the sequence in such a way that if n is even, then it will give you 3n by 2. If n is odd, then it will give you 3n plus 1 by 2. So if you are going to generate, if you are going to planning to generate all values of S2, then I can tell you here, like this is the first position, second position, third, fourth, fifth, sixth. So what I will tell, for the first position, you just choose n equal to 1. For second position, you will choose n equal to 2. So if you choose this accordingly, what the rules say, then you are able to generate all binaries of that S2. So if n is even, so if I'm choosing first position to be 1, then it is odd. So I will choose this value. Qn value is this 3, 1 plus 1 by 2, 2 will be cancelled out. So ultimately Qn value is 3. So how you decide Sn? Sn is if Qn is even, then it is 0. If it is odd, then it is 1. Since Q1 is coming is odd, so S1 is coming out to be 1. So that's why S2 first bit is 1. Similarly, for S2 second bit, S2 third bit, you can generate. So see what is the beauty, like just two line logic is there to define that sequence S2, which were looking like by observation, just you are not able to find that, okay, it is random or any logic is there. So the conclusion is that random sequence may not exist, what von Mises theory tells, because we don't know. At some certain level, some logic will come which will define those sequence. And at another hand, random sequence exist. We cannot prove that they exist. Means the second case is the CKS case. So ultimately, it came in form of the theorem. It is very famous theorem. Like there exist numbers having complexity greater than any mathematical system can prove. So you can't say that a given mathematical system is complete and it can do everything. So Chatin work is basically doing those things like how to define the complexity in defining in terms of the existence of numbers. So the idea here in the last 4-5 slide is to see the randomness in a finite sequence. And it has grown day by day too complex and clubbed in terms of the test suits, which will actually develop to give a confidence at certain level that, okay, the generated sequence is random or not. So if we see the categorizations based on the source of the randomness, like I already told, without merging of that natural source with a physical system, you can't build a secure system, which will give you a confidence for the security as well as the safety. So ultimately, the generation of those random numbers are very much important in all those systems. Now, how it has been categorized based on their development. So mostly I can tell that random number generators or random numbers generators means whatever the sequence we are talking earlier. So those systems is telling like the systems is generating random numbers. So it can be categorized in these two categories: pseudo random number generators and true random number generators. So and their definition is actually based on the previous results, like what logic you are using to generate those random numbers. So for pseudo random number generators, it is fine. Like Okay, you already know the mathematical logic. You already know that how long it will go to repeat, and based on that you can confidently tell, okay, this will generate a sequence which have no existing pattern till that much length. So that's well known, like by design or by knowing those key factors you can tell for their randomness. Another is true random number generators. So here the requirement of a physical source, or we can say that source of entropy, is interesting, where the idea of the uh, quantum world is playing interesting role, like how you absorb the source of entropy of a quantum phenomena, and based on that reading, or you can say measurement, you generate the sequence. So in between these 2 3 lines what I earlier told, there are quite interesting technologies playing key role, and they are they are giving confidence at certain level, like the 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 idea of randomness, how quantum technology is proving. So based on this confidence, this quantum random number generators playing the key roles in last uh, 2 decades. So people are working on that, and they are building those technology to read out the source of entropy and then generate a sequence which are in use for source of randomness for most of the it means commonly available cyber physical systems. So the question is that, like, if you generate those sequence, then based on these phenomena itself, whatever the sequence has been generated, and whether I should start using directly, or we will look inside that generated sequence also to see the available patterns. Because interestingly, the trust is the main question in um, all cyber security solutions, like at which level and how you build a trust, how you cyclically doing the test trust, and then find out, then come to the level of confidence or understanding. Okay, now I can use. So to do this, there are plenty of test suits, like it is the collection of some commonly available, or you can say that I can't say commonly available, because in those test suits some patterns are quite complex, which are looking in terms of all those sequence. So but mostly those test suits is collection of those observable patterns, and then verify that whether this is available in those generated sequence or not. So the smooth battery is one of the test suits where 12 statistical tests are there. Why I'm telling statistical test? Because they are looking in terms of the statistics of the binaries. For example, if I generated a binary sequence, then I can tell that whether number of ones and number of zeros are equal in that binary or not. So this is one of the statistics. There are so many other statistics also, and based on that, those uh, test suits has been proposed. Another test suits which is very famous is NIST test suits. So it contains 15 statistical properties, and it is testing those 15 statistical property and find out that whether in the generated sequence these properties are available or not. Similarly, die-hard battery, it is also containing it not exactly 15 but 15 to 20 statistical parameters they are looking inside that binary sequence. Similarly, entropy test, in short it is called an ENT battery, which contains 5 statistical properties. I will show you later like what type of statistical property it has. This very recent one, Boole test, which is based on the properties of Boolean function. Yeah, so any question? Yeah, some. Okay, so this Boole test is very recent, like on the properties of Boolean sequence. It has been developed to test the binaries generated from those random number generators. The scriptx is also an interesting itself. It is a complete package to test any crypto system. Like it will give you those statistical patterns not at the level of output and input. It will give you the test of the patterns inside the steps also, like after step 1, step 2, step 3, whatever the output you are receiving, on that it will applicable also. So mostly the question is ultimately like, what are the requirement to make test suits, or we can see in different way this problem. Like, okay, so since these 15 patterns they are looking, now whether some new patterns I am able to find out. So this is the interesting scenario. Like this is the scenario of in terms of the attacker. Like, okay, a very new pattern you are looking in that sequence. So if commonly available pattern you are seeing, then that's fine. That is available itself. But if something very new pattern you are looking inside that sequence, then this is a fresh case. So the first point is that like how you carefully choose that those new pattern what you are looking inside that sequence. So this is the first case. Test must be carefully chosen so that there are no dependent test. If you will not choose those things very carefully, then obviously you will come up with all those developed uh, uh, test suits and their subparameters. And the second point is that must have a solid mathematical theory. It means like whatever the patterns you are looking inside that, these patterns have some well-known mathematical theory. Like if this pattern will happen, then what are the loopholes, or what are the vulnerable situations you will face while generating those sequence. So majorly these 2 points is sufficient to see the randomness of a sequence. And the last one is like quite essential because efficiency. If you're if you are developed some technique to see a pattern which is finding out or looking out those pattern with very uh, computationally expensive way, then this will not work here because almost all those previous test suits I told, they are quite efficient. Like whatever the parameter they fixed to see in the binary sequence, they actually chosen those parameters in such a way so that those sequence will like you can easily or you can efficiently apply those tests and verify that okay, this generated sequence is random or not. So if you see one of the case like how those test suits has been designed, so I can tell like here what is the entropy test or what is the ANT test has been doing to test the uh, uh, generated binary sequence. So it has collection of 5 test suits. First one is the entropy test, second one is the chi-square test, arithmetic mean test, Monte Carlo estimation of phi, and serial correlations. So what each of these tests is doing, I'll just give you a brief idea about each of them. So in this entropy test or ENT test, actually the sequence has been divided in a finite ordered set sequence. And like if you have a binary, then the sequence is taken as a bytes, like each byte of the binary is to be one given to a one value. Similarly, next byte to be given to a value. So ultimately, the whole sequence is the values of number between 0 to 255. So using those their distributions in that sequence, you can calculate the entropy values. It means what their probability distribution and log of this probability distribution. So this formula will give you the entropy values of the particular generated binaries. So since I have chosen this to be byte-wise, so this entropy lies between 0 to 8. And based on this entropy value, you can directly tell that the generated sequence is random or not. So if the entropy is coming out to be close to 8, then you can tell that the sequence is non-compressible. It means you have less chance to compress the message available in that sequence. It means it is achieving its almost entropy. And if it is close to 0, it means like it has someone can easily find a pattern inside that and read the whole message. So this is the way of doing the entropy test in ENT test. But it is easily vulnerable, this test. It means it is not necessary like the entropy is coming out to be high, then I can tell directly that, oh, the sequence has that much strength that no one can find out any pattern, because you can easily fool that test. And the idea is just generate a sequence from 0 to 255 and repeat it with a cyclic shift. First generate 0 to 255, then start from 1, 2, 3 till 255, 0 similarly. So if you test this sequence with entropy test, then always you will get the entropy value close to 8. So in this way, you can easily fool this test. So come on to the next case. Next case is the chi-square test. What chi-square will do? So chi-square will do basically the comparison with some uniform distribution. So this x square, this x square is basically a ratio of the probability distribution or the average value what we are getting in those sequence. So you will get a chi-square value, and based on that chi-square value, you will get a p-value. And this p-value will help you to find out that whether this generated distribution, how far this generates distribution to be a uniform distribution. So the basic idea is to compare the generated distribution with a uniform distribution value. So in this way, you can build some other test suits also, because for the uniformly distributed sequence, the statistical theory has well explored, and they have well explored values of those parameters. That if things are uniformly distribution, then theory tells that this value should lie in between these two. So just compare those two things and find out that whether this is uniformly distributed or not. The third test is the arithmetic mean test. How this arithmetic mean test will work? So it is just telling about the arithmetic mean of those bytes. So if you see the byte values, then you can easily tell that 0 to 255 numbers are there. Then the average of this sequence is 127.5. It means you sum up the number from 0 to 255 and divided by 256. This value is come out to be 127.5. So it means whatever the sequence I will generate, I just find out, I convert them in the bytes, integers, and then I find out the average. If this average is close to be 127.5, then I can tell that this is satisfying this condition of arithmetic mean. If it is less than that, then I can tell that, oh, some number is repeating in this whole binary with some greater frequency. So this is again a vulnerability, and then we can tell that we are able to find a pattern. In Monte Carlo estimation of pi, this idea is interesting. Here, the thing is that like how you will approximate the value of pi using those random sequence. So what you will do, you will generate those binary sequence and based on the generated binary sequence, you distribute in the y-axis and x-axis. So you divide those binary sequence in two-dimensional array and pick the points from one array to second array, one array and second array. You will get a pair. And these pair can be represented as in first quarter of the Cartesian plane. So choose the random points and locate in the Cartesian plane. You will do it exhaustively for whatever the numbers you generated. So ultimately what it will do, it will first quarter of the XY plane is basically a 1/4 of a circle. So you just point all those which is lying inside that circle based on your generated random number and the total points which is coming in a rectangle, because I have taken a point from 0 to 2 to the power 24 minus 1 in x-axis. Similarly, in y-axis, 0 to 2 to the power 4 minus 1. So if you see the end point and match those lines, so one line is parallel to x-axis, which is y is equal to 2 to the power 24 minus 1. And one line is parallel to y-axis is x equal to 2 to the power 24 minus 1. So the intersection of these four lines will give you a rectangle, and a semicircle would be there, which is in such a way like its radius is 2 to the power 24 minus 1. So there is a geometry which will tell you inside that square you have a 1/4 of a circle, and you are just locating the points inside that square. So ultimately, the point will come inside that circle. Some point will come at the boundary of that circle, which is lying inside that square also. So it will cover the whole circle. Now the question is that if it will cover the whole circle, then it is almost equal to the area of that circle. So it is approximated to the area of the partial ball and area of the rectangle. Then finally, if you divide this theoretical value, then it will come out to be pi by 4. So if we settle down the first ratio to be the last ratio, which is pi by 4, then the value of the pi will come out to be 4 into point inside the circle and total points. So since you know that how many points you have getting inside the circle and what are the total points you have taken, so you can easily calculate this value and see that whether it is matching with the value of the pi or not. If it is not matching, then there is a pattern, because the pi is completely irrational number. So the theory tells like since it is irrational, so you can't justify that any easily observable sequence can generate the values of the pi. So that is the logic behind the Monte Carlo estimation. Serial correlation is like how independent the immediate preceding bytes are there. So to do that testing, they are doing the Pearson correlation coefficient, just first bytes to the next byte like that. And if it is close to 1, then it is correlated. If it's close to 0, it is uncorrelated. So the correlation coefficient theory is well known. So based on that, they are able to find out the binaries which are generating are correlated. Now the question is that how the NIST battery test is performing. So the NIST, I already told like it has 15 to 16 or 15 to 20, you can tell like these set of statistical patterns they are looking inside the sequence. So how those sequences are working and how those what those tests are there, and since it is widely usable because NIST has standardized it, and then in terms of so many standards, people are following it to verify the randomness of a generated file. So basically, what the parameters are there in NIST test suits we can see using that table. So the idea is that you actually working on the hypothesis like whether the generated data is random or not. Suppose this H naught, it means which is my null hypothesis, which is called as data is random. Then obviously the alternative thing is that data is not random. So these two hypotheses and their situation in testing will generate these four cases. Because what are my hypotheses and what are my conclusion? So both have always two options. So their combination will generate you four options. So first one is, the first case is if data is random and it's not is true. So the conclusion is coming like if data is random and my hypothesis is coming out to be true, then this case is comes under like, okay, no error is there. Like, okay, that's fine. The second case is that data is random, but H naught is not true. It means whatever the hypothesis I built and I run out the binaries and I find out that it is coming out to be like this hypothesis is not valid. Then this is the case of the type 1 error. Similarly, the second case, if data is not random, and the alternative hypothesis is true, it means data is not random, then I'm accepting the alternative, which is already telling that data is not random, then there is no error. But the reverse case is that data is not random, but null hypothesis is going out to be true, then this is called as type 2 error. So the no error case is fine, but what are these two, type 1 and type 2 error? Because based on these two uh, 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 class of errors, the NIST parameters has been defined. So the ultimate objective is there, like how I find out the probability of type 1 error. So simply, like whatever the error is coming, this error probability should come out to be very less. If there's error probability is come out to be very less, then my test is robust. So there are two parameters, alpha and beta. Alpha is that the probability of type 1 error, and beta is the another probability which is called as type 2 error. So after running those tests, what is the probability I'm getting type 1 error? What is the probability of type 2 error? So this is the main parameter to set all those tests, 15 tests in the test. So ultimately, if we say that what are the parameters, then alpha, beta, and size n. And it means what is the size of the sequence you are taking. So we have to choose these three things widely. But the problem is with NIST test suite is that it will give you freedom to choose only n and alpha, not beta. So only whatever the library is available, it's giving you to choose only n and alpha, not beta. So whenever you are looking to build some new set of pattern, then you have to think about the availability of alpha, beta, and n. Then only you can start to justify that, okay, this test is working fine. So normally what NIST suggests is to choose alpha in the range of 0.001 to 0.01. This range is there. It is very negligible. Like this probability will come out to be very less. Out of 1,000, it may come only one. Means out of 1,000 sequence, only one will give you that type of error. So that is the case of choosing alpha. And based on the choice of alpha, you will decide from the p-value that the generated sequence is a random or not. So this probability will come out to be very less. Like this type 1, type 2 error you are receiving in very less count, then only you can tell that the sequence is random or not. And how you calculate the p-value? So the ERFC function is there, which is the Gauss distribution based on uniform distribution theory, and you can easily find the ERFC value. So while while implementing those tests, you require those things. But if you are using directly what NIST library is giving, then you have to choose alpha and n, and based on that you can verify. So some of the common tests are there here. First one is the frequency test, which is called monobit test. It is telling about the proportion of 0 and 1 in the sequence. Similarly, frequency test within a block. It means rather than seeing the full file, you're just seeing in a block. The run test, it means you are looking the runs of 0 and 1, like 0, 0, 0, 1, 1, 1, how many of these type of sequence are there. Similarly, long run of a 1 in a block. So these are the different tests in the NIST library. Binary matrix rank test, it means you generate a matrix based on those binary and see their rank. Discrete Fourier transform test, which will give you the Fourier transformation of those binary, and you will see that whether those Fourier transformation is flat, it means uniform or not. These are the other test cases. This is interesting, that linear complexity test. If a sequence was random, then it would have long LFSR. It means the LFSR is well-known design pseudo-random number generator. So what inside that test is that you just generate a random sequence and give this as input to LFSR and see that how long it will generate a random sequence. So from a random sequence, you are giving it to another random sequence and seeing their pattern. For another random sequence, you know their properties, you well studied it, so you're just feeding the generated random sequence to another random sequence which you know earlier. Based on this study, you will be able to find out their pattern. Approximate entropy test is same what there in the ENT test. Cumulative sum test, it means you generating a sequence by adding those binary, first 2 binary, first 3 binary, first 4 binary, first 5, just you are adding and you generate a sequence, and in that sequence you're looking at pattern. Random exertion test, random exertion variant test. So ultimately this will cover all those 15 things what are available, and they are looking for those binaries. So this is the comprehensive table, like where and what each test suits are giving in terms of the benefit as well as in terms of disadvantage. So if you see the NIST, the disadvantage is the fixed parameter. And there are dependencies between tests. So at some case, you will find the same result for two set of tests in NIST. So That are the disadvantages. Now come to the Boole test. So I will just brief that how this Boole test is working, and I will show you some statistical results what we published in extending those properties of Boole test. Then I'll wind up that. So basically in Boole test, what is happening? It is like a generalization of monobit test available in NEST. So monobit test is doing the computation of or the enumeration of 1 and 0 and see that whether they are balanced or not. So the same monobit test I can see in different way. Different way in such a way like, suppose I generated a binary. What I'll do, I'll pass those binary to a 1-bit Boolean function. 1-bit Boolean function, it means fx equal to x. So if fx equal to x, then whatever the input for f, the same output I will get. It means if the input is balanced, then output will also be balanced. But what if I will go to two variable Boolean function, not fx equal to x, fx comma y equal to x comma y, or fx comma y is x XOR y. So if we'll feed those binary to that Boolean function, then I will not get the same output. Then I will measure that whether the output is still looking the same what input is there or what change we can observe. So that is the second case. So monobit test is doing the same thing, like a Boolean functions chosen specifically and feeding the input to the feeding the output of a random sequence to that chosen Boolean function, generate the output and observe the pattern in that. So that is the case is happening in the binary sequence of uh, any random number generators. Another set of thing is like how you will see the cryptographic properties of generated sequence. So the cryptographic properties is basically well-known study of those binary sequence. You generate a binary sequence and the well-established theory is there, like what type of properties is required in a binary sequence to say that it is cryptographically secure. So explore those properties and see that whether these properties is available in generated sequence or not. Under what set of parameters. So non-linearity of a binary sequence is very much important cryptographic properties. You can compute it for any even length binary sequence. And you can observe the pattern at the output level that whether this pattern is achieving the good non-linearity or not. So we have done this for some set of binary sequence generated by our in-house random number generators, some true random number generators, and some quantum random number generators, and some pseudo random number generators also. Apply those tests, like how many of them are achieving good nonlinearity. But doing this is quite expensive in terms of computation. For largest length of the bits, it is quite expensive. So here, if you see that, so nonlinearity is a value. It means you, for any set of binary sequence, it will come out to be a fixed value. Suppose the binary sequence of 8-bit, then nonlinearity can may come like 3, 4, 2, like this. So we have done it for the quantum random number generators and true random number generators. Their comparison is there. It is showing in the graph. Like how many binary sequence is achieving good nonlinearity. So these are just use case. Like you can observe that the graphical presentation, that how you can compare the two generated binary sequence in terms of one cryptographic properties, like which is better and which is not. This is just a coefficient what I discussed here based on the nonlinearity. And based on this coefficient itself, you are able to tell that, okay, which is better generator of non-linear sequence, not a linear sequence. So we have done it for QRNG and TRNG. It is published work. I hope, like, if you want, then you can find out that paper. It is available in my webpage also. And these results were also available. Similar way, we have explored some the combination of two cryptographic properties. First one is the balance property, what is there in the monobit test. And second one is that it's differential property. Differential, you can say that a type of permutation, you can tell, like how you reorder a binary sequence. So we have done the experiment for that particular sequence itself. So we named it like linear balanced sequence. It means there are two properties. First one is the linearity, and second one is the balanceness. So if you club these two properties, then there are not that much binary sequence which will satisfy these two properties simultaneously. So you're able to count those. So this is one of the result, like for 8-bit sequence, there are only 56 binary sequence are there out of 2 to the power 8 sequence. You understand? For 8-bit sequence, how many total sequence are there? 2 to the power 8. So out of this 2 to the power 8, only 56 binaries will satisfy that property. Similarly, for 4-bit sequence, you will get only 396 binaries of 16-bit, which will satisfy that property. So the first point is that how to fix those cryptographic properties. This work is also published. You can get it from the published work. So the thing is that how to fix those cryptographic properties and then find out some statistics for those binary sequence. And then after model a test, which will give you the results for finding some pattern. So these two tests we have applied. Like first one is a long run linear balanced Boolean test. Another one is linear balanced Boolean test. The meaning of these two tests is simple, like whatever the sequence we fixed for some properties, we are looking that whatever the random number generators I am choosing, whether it is able to generate all those sequence or not, and how early it will generate. How early it means how fast. So we have done some experiment also. Here you can see that the row part is the name of the random number generators, and the column is the number of rounds you have to perform to generate those fixed set of binaries which are cryptographically good. So we are able to find that okay, this for this random number generator, which is MRG32K3A, is achieving very fast those binary sequence which are cryptographically good. The second test is basically telling about that what is the distribution of those sequence. It means if I assume that only 4-bit sequence, 8-bit sequence I'm using. So for 8-bit sequence, 2 to the power 8 possible sequence are there. So what I'll take 2 to the power 8-bit binary, which is coming from a source of some random source. In that binary, I'm looking at how many of them are cryptographically good or linear balanced. So in this way, the distribution is following for this particular graph. This is mostly like uniformly, but outliers are more in case of Shake 256, Salsa 20, and QRM, and as well as in ACE 128. So this is just an experimental result, like how you apply cryptographic properties on a binary and see how those properties following by the quantum random number generator, true random number generator, or pseudo. Based on that, you are able to tell that, okay, this is generating good binaries in terms of those cryptographic properties. So it is useful in case of the random seeds for any cyber physical system. And in terms of the testing of those binaries for generation of random numbers. So this is just a set of problems raised from the patterns finding in those binaries, as well as the cryptographic use. Because cryptographic use is specifically about the good source of the sequence. So, and whatever the sequence you are generating, those sequence must be cryptographically strong. Then only you can tell that, okay, this this is coming from a well-designed algorithm. So that is the overall picture of this particular, the randomness as well as the testing. These are some reference. And finally, this is the time for asking question. If you have any question, then you can please ask.
Any questions? Please unmute your audio and you can ask. So, thank you so much, Dr. Shashikant sir, for your patience in explaining in detail the concept and the calculations behind the random number generators. On behalf of the management, the faculty, and the organizing team of this FDP, ATAL sponsored FDP on quantum computing and quantum machine learning, I extend my heartfelt thanks to you. Thank you.
Thank you, ma'am. Thank you. Thank you, everyone. So I may leave now, yeah?
For the participants, we will meet again for the third day tomorrow at 6 o'clock, 6 p.m. Also, we'll be having again two sessions, one by Dr. Ankur Raina and another by Dr. Alien Jams. So kindly join us. And this is Deepa signing off for today. Thank you. Have a good day.